So in the previous session, okay, so what things we have discussed? So we had started with the nucleophilic substitution reactions. Okay, so these nucleophilic substitution reactions, these are of two types. Okay, so we have seen SN1, okay, SN1 mechanism and SN2 mechanism. What is SN1? Substitution nucleophilic unimolecular. And what is SN2? Substitution nucleophilic bimolecular. Okay. So what is SN1 mechanism? So SN1 mechanism, it is a two-step mechanism. Okay. And the rate of the reaction, it depends upon the it depends upon the concentration of only substrate. Okay. And that is your alkyl halide. Okay. So this is a first order kinetics. It follows what? First order kinetic. So in SN1 mechanism, as it follows two steps, first step is a slow step, okay, which leads to the formation of carbocation, and second step, the fast step, where attack of nucleophile takes place on the carbocation, okay, and you get the substituted product, that is alcohol. Okay, so from alkyl halide, okay, you are getting a alcohol, tertiary alcohol. So this is a SN1 mechanism. So when we are seeing the SN1 mechanism reactivity of the alkyl halides, tertiary alkyl halides are more stable, then secondary, then primary, and then the methyl carbocation. Okay. Then we had, so these were the note. Okay. And in SN1 mechanism, okay, it shows a racemization. What do you mean by racemization? So it will have 50%. The attack is possible from both the side, either from back side or can the front side. So if it attacks from the front side, that is called as retention of configuration. If it attacks from the back side or the behind, then it is called as inversion of configuration. Okay. So here, when 50% inversion plus 50% retention is there, then it is called as what? Racemization. Okay. So this is on from stereochemical aspect, so that we are going to study today. Then what is SN2 mechanism? Okay, that is bimolecular nucleophilic substitution. So these reactions, okay, in SN2 mechanism, so it is a one-step mechanism, okay, and it follows what? Second order kinetics. So the rate of the reaction depends on the concentration of the alkyl halide and the nucleophile, okay. So in SN2 mechanism, what is possible? Inversion of configuration is possible. Okay. So this inversion, what it is called as? It is called as levorotatory. Okay. It is called as it is called as Walden inversion. So the inversion of configuration which occurs during SN2 mechanism is called as what? Walden inversion. Okay. So SN1 mechanism, how the mechanism takes place? SN1 mechanism. So the attack of the nucleophile takes place from the backside of the carbon. Then it undergoes a transition state where formation of bond and breaking of bond takes place simultaneously. Okay. And thus, what will happen as a new bond is forming, the old bond is broken and you get the substituted product, which is a inverted product. Okay. Inverted product is obtained. Okay. So this is 100% inverted product. So this inversion is called as Walden inversion. Then when we are discussing about the features of SN2 mechanism, as we know, SN2 mechanism, it follows a one step, okay, wherein it undergoes via a transition step. So it undergoes the SN2 mechanism, it undergoes via what step? It undergoes via transition, okay. It undergoes via a transition state. So making of bond and breaking of bond takes simultaneously. Now, when we are talking about the reactivity of halides towards the SN2 mechanism, primary alkyl halides are more stable, then secondary, then tertiary alkyl halides. Okay. So this is about the what? This is about your SN2 mechanism. Okay. So today we are going to start with the stereochemical aspects of nucleophilic substitution reaction. Okay, what we are going to start today? We are going to start with the nucleophilic substitution, that is stereochemical aspects of nucleophilic substitution reactions. Okay. So these are some of the important terms and some of the notations which we are going to discuss when we are studying the stereochemical aspects. Okay. Now, the first common, so these are some of the important principles on which our stereochemistry depends. Okay. Now, before going for the stereochemical aspect, can you tell me what do you mean by stereochemistry, students? Stereochemistry. Yes, what do you mean by stereochemistry? So it in stereochemistry, what you are studying? You are studying the different spatial arrangement, okay, of the atoms in a molecules. How the different atoms in a molecule are arranged, okay, in the spatially in the space, okay. So like that, we are going to study some of the stereochemical aspects of these nucleophilic substitution reaction. So the important terms which we are going to discuss is first one is the plane polarized light, okay. Now, what do you mean by a plane polarized light? Okay. Now, okay. So here, what do you mean by a plane polarized light? So suppose you have a ordinary light. Okay. You have a ordinary light. This ordinary light, okay, it consists of waves which are vibrating in all the directions. Okay. So this you might have studied in physics. Okay. But still, we are going to study here also. So a normal light, okay, when a normal light, you're taking a normal light, suppose from the bulb, okay. So the light which is produced, so the rays, okay, they vibrate in all the directions. So so beam of light, when the beam of light falls, so this beam of light, it consists of waves which are vibrating in all the direction. Now this your vibrating wave, okay, when you pass through a nickel prism, okay, so it is a prism which is called as a nickel prism. So this nickel prism, if you pass it, what will happen? The rays which are vibrating or the waves which are vibrating in all the direction, they become plane polarized. So they will all vibrate in a only one direction. Okay, so this is called as plane polarized light. So what is done? So from a beam of ordinary light, which consists of a waves which are vibrating in all the direction. Okay, it is passed to a nickel prism, and when it is passed to a nickel prism, so then the waves, what happens? So they start vibrating in a they start vibrating or they start to move in a straight line. Okay, in a plane polarized manner. Okay, so this is called as what? This is called as plane polarized light. Okay, so this is the meaning of plane polarized light. So what we are doing, we are taking an ordinary light and we are passing through a nickel prism. So when you pass through a nickel prism, whatever the waves which are vibrating in all the direction, they are made to vibrate in a one possible manner. Okay, so this is about plane polarized light. So the what is so there is one more which is called as optical activity. Okay, now what do you mean by optical activity? So the solutions of some of the organic compounds. Okay, so there are some of the solution of organic compounds. Okay, which have the ability. Okay, they have the ability to rotate this plane polarized light. Okay, and such compounds are called as optically active. What they are called as? They are called as optically active. Why they are called as optically active? So some of the compounds, okay, some of the organic compounds, they have the ability. They have that ability to rotate this plane polarized light, okay. So whatever the plane polarized light is there, okay, so this plane polarized light. So either they have the ability to rotate it to right side or they have the ability to rotate it in the left side. So this is called as what? They are called as optically active. Okay. And the property is called as optical activity. And what the property is called as optical activity. Okay. So these are the important terms which we are going to use in this stereochemical aspects. Okay. Next is there is something called as dextro and levorotatory. Okay, there's something called as dextro and levorotatory. So let me write here itself. So what is dextro and levorotatory? Dextro-rotatory and levo-rotatory. So these are two different terms, dextro-rotatory and levo-rotatory. Okay. Now, whenever, so as we have discussed, what is optical activity? So some of the organic compound, they have the ability to rotate the plane polarized light towards the right side, that is in the clockwise manner. How the clockwise moves? Like this, right? And if some of the compounds have the ability to rotate it into the left side, okay, that is anti-clockwise, then so such compounds, okay, so they are called as optically active. Now, so the compounds which rotate the plane polarized light towards right side. So if the plane polarized, now this is plane polarized light, okay, it will vibrate in a one direction, straight direction. If it rotates to the right side, if it rotates to the right side, then what it is called as? It is called as what? It is called as dextro-rotatory. What it is called as? Dextro-rotatory. Okay, it is called as dextro-rotatory. Okay. Then if the and dextrorotatory, or they are called as deform. They are called as what? Deformed substances. Deformed substances. Okay. Next, levorotatory. So, and before that, so dextrorotatory, they are what? Indicated by plus sign. Okay, they are indicated by plus sign or small d. Small d in front of their names. For example, okay, if the compounds are rotating towards the right side, so it is plus, okay, if it is written like this, means what? The compound lactic acid, the molecule lactic acid, okay, it is rotating in the right side. It is rotating in what? It is rotating in the right side. Okay, so it is called as dextrorotatory. So this indicates that it is rotating in the right side. Okay. Now levorotatory, so the compounds which rotate the plane polarized light towards the left side, okay, towards the left side or anti-clockwise, or what? Anti-clockwise, then they are called as what? They are called as levorotatory. Okay, levorotatory, or they are called as L form. Okay, and these are indicated by what sign? Minus sign, and they L is written. Okay, L is written in front of their name. For example, okay, for example, minus, okay, minus lactic acid. Okay, minus lactic acid. Understood what is dextrorotatory and what is levorotatory? So whenever the compounds, okay, have the ability to rotate the plane polarized light towards right side, then they're called as dextrorotatory. And when the ability of the molecules or the compounds to rotate the plane polarized light towards the left side, then they're called as what? Then they are called as levorotatory. Okay, is it clear up to here?
Yes, ma'am.
Okay. I hope others have also understood. Okay. So optical plane polarized light, we have seen what is, okay, what is plane polarized light. Then we have discussed what is optical activity. Okay. Then we have discussed optical activity. Then we have discussed what is dextrorotatory and what is levorotatory. Okay. So next we are going to study what is optical isomerism. Okay, optical activity. Fine. See here, what is optical activity? Now, plane polarized light is understood. See, whenever a beam of light, okay, which is passed through a normal ordinary light, okay, it vibrates in all the direction. So there is a prism, okay, there is a prism which is called as a nickel prism. So when you pass the ordinary light through this nickel prism, what will happen? as you can see, the different beam of light, it is moving or it is propagating in all the direction. So it is made, when it is made to pass through this nickel prism, it vibrates in same direction, okay, in the straight direction like this. Now, some of the organic compounds. Now, when this is a plane polarized light, okay, now this is a plane polarized light. Now, this plane polarized light, so some of the compounds, okay, some of the compounds, what they have the ability to rotate this plane polarized light, okay, they have the ability to rotate plane polarized light. So, if they rotate the plane polarized light, so such a property is called as what? Optical activity. Okay, so such property shown by the compounds, it is called as what? Optical activity. Optical, they are said to be optical active, and the property is called as optical activity. Now, if that compounds rotate the plane polarized light towards right side, then they are dextro-rotatory, and if they rotate the plane polarized light towards left side, then they are called as levo-rotatory. These are indicated by plus sign or small d. This is indicated by minus sign or L. Okay, and this undergoes anti-clockwise direction, and this shows clockwise direction. Okay, so like this you have to remember. Next, we are going to see the optical isomerism. Okay, next is the optical isomerism. So compounds which are having same molecular formula and structural formula, but they differ in the rotation of plane polarized light. Okay, then they are said to be optical isomers. So as we have said, so the compounds now plus lactic acid and minus lactic acid. Okay, so these compounds are same. Okay, these compounds are same. Their molecular formula is also same. Okay, their molecular formula is also same and structural formula is also same. Where it differs in the direction of rotation. Okay, it differs in what? It differs in direction of rotation. So how is the direction of rotation? See here. So COOH. Okay. Now here C CH3 CHOH. Okay, and here COOH COH H and CH3. So this is minus. So this is a plus lactic acid and this is a minus lactic acid. Okay. So what is happening? So here the compounds. So here the compounds you can see in the both the condition that they are having same molecular formula. Is there any difference in the molecular formula? No. The structural formula is also same. Only what? The way of direction. Okay. The direction of the rotation. That is how the plane polarized light has rotated. Okay. Whether it is in right side or in the left side, then they are said to be optical isomer. Okay, so these are the pairs of optical isomers and the phenomena is called as what? Optical isomerism. So plus lactic acid and minus lactic acid. So this is optical isomerism. Same molecular formula, same structural formula, differs in the direction of rotation of plane polarized light. So the example is plus lactic acid and minus lactic acid. Okay. Fine. So next is chiral center or asymmetric center. Okay, next is what? Chiral center or asymmetric center. So the arrangement of four different groups. Okay, so I'll show you. So if you have, so the arrangement of four different groups around the center carbon. Okay, around the center carbon. Okay, then what is it? Is a tetrahedral, and if all the substituents attached to that carbon is different, then such a carbon is called as chiral center or asymmetric center, or it is called as stereo center. Okay, now what do you mean by chiral carbon? So this is a center carbon. So to this center carbon, so these are the four different groups, and these four different groups are different. You can see the four groups are different. So to the center carbon, if the four groups are different, then this carbon is said to be a chiral center. Okay, it is called as chiral center or asymmetric center, or it is called as stereo center. Okay, very important. What is chiral center? So the arrangement of four different groups. So tetrahedral means what? Like this. So in the tetrahedral manner. Okay. Suppose I take OH here, I take COOH here, here I take H, and here I take CH3. So what you can see across the tetrahedral carbon in the center carbon, you can see the four different substituents are attached to the four corners of tetrahedral. Okay. So this carbon is said to be a chiral carbon, a symmetric carbon, or a stereo center. Okay. So these are the important terms. So please, I hope you are noting down the things. Very important stereochemical aspects. Okay. So here you can see the chirality. No, here we are not considering for double bond system or anything. Okay, it will be for like a molecules with single bonds itself. So okay, we are just seeing into pictures about the molecules. Okay, with a tetrahedral. We don't consider here double bond system. Okay. So next is optical isomers. We have seen. Okay, chiral center. Okay. Next is chirality. Okay. Next is what? Chirality. So now suppose now what you do? Hmm. So if I take my any object, okay, if I take a object, suppose I take my one palm, okay. Now this palm, what I'll do with another palm, okay. Can I put one on one, whether it is like whether it is placing or like your thumb on the second thumb itself? No, right? It is not. This word is called as superimposable. Is it superimposable? Is it falling on one another? If you take your one palm and try to put it on the another palm, okay, like this. Is your this finger, okay, right hand thumb, is it coinciding with your right left side thumb? Yes, no, right? So it is not superimposable, right? So an object or a molecule which is not superimposable on its mirror image, it is called as what? Chiral. Okay, and this property is called as chirality. So whenever you're taking any molecule, okay, or whenever you're taking any object, so if this object or the molecule, it is not superimposable. What do you mean by superimposable? Okay, you take your palm itself, two palms. So what you do, you take your one palm and try to put on the another. So see whether you are both the thumbs, that is your left hand thumb is coinciding with the right hand thumb and the other fingers. Okay, so no. So this such a compound, this property, it is called as what? Chirality. Okay, so this is called as chirality. So you can see that. So these two compounds, so what they have done, so this is a molecule. Okay, so you can see there are four different colors, right? Black, green, blue, and red. So what it indicates? It indicates that there are four different groups. So this carbon is called as what? Chiral carbon. Okay, so this carbon is a chiral carbon. So this chiral carbon, what they have done, they have taken a mirror image of that. So when you take a mirror image of that, okay, so I'm taking a mirror image. So this is a mirror image of that. Now what I'll do after taking a mirror image, I'll place the first molecule on the second. So whether it is impossible? No, it is not superimposable. Okay. So such a property of the molecules is said to be chirality. Okay. It is said to be what? Chirality. So what is chirality? So object or a molecule which is not superimposable on its mirror image is called as what? Is called as chiral, and this property is called as chirality. Okay, so you can see that A and B cannot be superimposed. So if I take the two mirrors, okay, two mirror images of the two molecules, and if I try to merge them one on the above, they are not superimposed. Okay, so these are said to be chiral and they are called as enantiomers. So there is one more term which is called as enantiomers. Okay, so before that, what is a chiral? Okay, so object or a molecule which are superimposable on their mirror image is called as a achiral molecule. Now for chiral molecule was what? For carbon, okay, four different groups are attached. Four different groups are attached. So such a carbon is called as chiral. Okay, now for a carbon, okay, so there are no four different groups are attached. Any one at least is repeated here, right? So this is a chiral center. This is a chiral center, okay, or it is called a chiral carbon or a chiral center or symmetric center, okay. So in this, what is possible? That the molecules will be superimposable. They are superimposable on their mirror images. So such a molecules, they are called as what? A chiral molecule, okay. So these are some of the examples. Now, if I take the examples of chirality, so let me take some examples of chirality so that it will be more clear to you. Okay. Now here, so if I take this compound, that is CH3, okay, CH2, CH3, and Cl. So can you tell me which is the chiral center? Yes, which is the chiral carbon, which is having the chiral carbon?
CH.
Yes, CH, right? Because here you can see that C and H. So here you can see there are four different groups attached, right? Now for this carbon, if I talk about the second carbon, so here CH2. So what will happen? H and H. So same carbon. So this is a chiral. Now here CH3. So three hydrogens. No, wrong. So only there is one chiral center is possible. That is at CH. Okay. So let me take the second example. CH2, OH, CHOH, and CHO. Okay. Here, yes. This carbon, right? So this carbon is a stereo center. Okay. So it has a stereo center with four different groups. Okay. So this is one group, here one, here. So when you talk about here, so this will be C double bond OH1, 2, 3. Okay. So this is a sp2 planar. So this won't be possible. Then next one more will take. Here, so this is the stereo center. One more, CH3, CH, COOH, and OH.
MCH.
Yes. So this is your chiral center. So these are the chirality. So whenever any object or a molecule, okay, it is not superimposable on its mirror image, okay, is called as a chiral, and this property is called as chirality. Okay. And the molecules or object which are superimposable on their mirror image, then they are called as what? Achiral. They are called as achiral. For example, so let me take an example for this also. So if I take an example of propane to all, okay, propane to all, what is the structure? CH3, CH, OH, and CH3. Okay, 1, 2, 3, propane, 2, and all. Okay. So propane to all. So let me write the structure. So CH3, CH3, H, and OH. So let me take the mirror image of this. So what will happen? So this will become flip. Okay. So here it will be CH3. Here it will be CH3. And this will become H. Okay. So these are A and B. Now what I'll do? Now this I will rotate by 180 degree. Okay, so after rotating by 180 degree, this will move this side. So this will become OH, C. This will become uh, CH3. Here it will be CH3 and here H. So here A and this is similar, right? So you can see that the object or the molecules are superimposable on their mirror image. So such objects are called as what? A chiral molecule. So what we have done, we have taken molecule A, we have taken the mirror image of that. Then after taking the mirror image, we have flipped it by 180 degree. So after flipping 180 degree, this will come this side, this will move this side. So you can see, so A and C are similar. Okay, A and C are similar. So propane to all, it does not contain any asymmetric carbon. Okay, there is no asymmetric carbon. Why? Because there are two CH3 groups. So it is not a asymmetric carbon or a chiral carbon. Because there are no four different groups attached to this tetrahedral carbon, because there are four different atoms attached to this carbon.
क्या बना
Okay, so as there are four, so there are no four different groups attached, so hence it is called as a chiral. It is called as what? A chiral molecule. Is it clear up to here? Yes.
Yes, ma'am.
Okay. I hope others are also understanding. Yes, you are.
Yes, ma'am.
Okay.
Yes, ma'am.
Fine. Okay. So next is enantiomers. Very important. Please mark it important for 2 marks. Okay. So important definition asked from stereochemical aspects. Also dextro and levorotatory. Okay. Whatever I discussed about dextro and levorotatory. So the compounds which rotate the plane polarized right towards right side, dextrorotatory. Okay. Or it is right side or clockwise direction. And if the compounds are rotating the plane polarized right towards anti-clockwise direction or left side, then they are called as what? Levorotatory. Okay. So these all things, so very important, dextro and revo, then is the enantiomers. Okay, so with examples. So whenever you're doing any definition, you have to do with examples. Next is enantiomers. Okay, now what do you mean by enantiomers? Now we know what are stereocenter. Okay, so stereoisomers. Stereoisomers means what? So the carbon having four different groups. Okay, so the stereoisomers which are non-superimposable. So when the molecules are non-superimposable, they are not superimposed on their mirror images, such stereoisomers, they are called as enantiomers. What they are called as? They are called as enantiomers. So the stereoisomers which are non-superimposable on their mirror images are called as enantiomers. So these are the enantiomers of aniline. Okay, these are the enantiomers of aniline. Okay, so when you take the mirror image, okay, so these are the mirror image of each other. So these are non-super. So when I take this molecule and I take the mirror image and I place one on this, okay, suppose this is the H. So this is what? NH2 and this is CH3. Now this is your R aniline. So what I'll do on this, I'm putting this molecule. So I'll take another color, COOH, okay, and here will be your NHH, and here will be your NH2, and here will be your CH3. So is it superimposable? No, they are non-superimposable on their mirror image. So such a molecule, stereoisomers, they are called as what? Enantiomers. So let me take some more examples of enantiomers. So examples are very important. Lactic acid. Okay, lactic acid. So COOH, CH, then OH, CH3. Okay, take the mirror image. So COH, CH, CH3, and OH. So this is a minus lactic acid. Again, this is a plus lactic acid. Okay, so these are the enantiomers. Then next is butane to all. Butane to all. So your CH3, C2H5, okay, HOH, take the this of that, CH3, C2H5 and H. Okay, so this is a minus and this is plus. So plus butane to all, and this is minus butane to all. Okay, so these are the examples of stereo isomers. Okay, that is your enantiomers. So enantiomers, they have identical physical properties. So they are both these enantiomers. Okay, these are pair, right? These are the pairs of enantiomer. So these enantiomers, they have identical physical properties. Like they have same boiling point. Okay, they have same melting point. Their refractive index is same. Okay, their refractive index is also nearby same. But where they differ, they differ only in the direction of rotation of plane polarized light. So direction of rotation of plane polarized light. So these are the properties of enantiomers. So their physical properties are same. Their physical properties are same. Only where they differ in the direction. Okay, how the plane polarized light has rotated. So if it is rotated in the right hand side, then it is clockwise direction. Then it is what? Dextro. If the compounds have rotated the plane polarized light in the anti-clockwise direction, then they are called as levorotatory. Okay, so the enantiomers, they differ only in the direction of plane polarized light, rotation of plane polarized light. Okay. Next is racemic mixture. So this we have already studied. So let us study the definition of racemic mixture. Important. Mark this also as important. Okay. So mark this as important. What is racemic mixture? So a equimolar mixture. Equimolar means what? Equimolar, equally. Okay, present equally. That is 50% dextro and 50% levo. Okay, 50% dextro and 50% levo rotatory substance. It is called as racemic mixture, or it is called as racemic modification, or it is called as what? Racemic modification. So a equimolar mixture, when you have 50% dextro and 50% levorotatory substance, such a mixture, it is called as a racemic mixture. So what will be the rotation? Optical rotation. So when you have, okay, when you have equally, so that is, this is what it will be. So this will cancel this, right? So when you have 50% dextrorotatory and 50% levorotatory, what will happen to the optical isomer? It will be 0. Okay, so the optical rotation will be 0 because the rotation of one isomer will be balanced by the rotation of other isomer. So how it is denoted? It is denoted by plus or minus lactic acid. Okay, so like this. So this is a racemic mixture. So when you are writing racemic mixture, it will be plus or minus, or you will write DNL lactic acid. Okay, DNL lactic acid, or you can write plus or minus butane to all. So these are the examples of what? Racemic mixture. So 50% equimolar. It is present in equal uh, equal amount. Okay, that is 50% dextro, 50% levo. So what is the optical rotation of racemic mixture? It is 0 because the rotation which is created by one isomer will be balanced by the rotation of another isomer. Okay, so the maximum number of optical active isomers for a compound with stereo center n, we can be calculated by 2 raised to n. Okay, so how much number of stereo centers are present for optical active isomer can be calculated by 2 raised to n. So this is about racemic mixture. Okay. Next is meso compound. So next, one more term, meso compounds. Now, what are these meso compounds? So you can see the example. Yes. So here you can see. So this is a meso tartaric acid. So this is an example of what? Meso tartaric acid. Okay, tartaric acid. So what you can see, so this is a molecule. Okay, now what they have done, they have put a mirror here. Okay, they have put a, or you can put a plane of symmetry. Okay, plane of symmetry. You put a line here. So what you can put, what you can do, just put your hand on that molecule like that. Okay, in the center. What you can see that the above half and the below half are the same, right? So what is happening here? So the molecules which contain a plane of symmetry, okay, what it does when you have a plane of symmetry in a molecule, it will divide the molecule into two half, right? So this is a one half and this is a another half. So this is a another half, right? So this is one half, this is another half. So whenever there is a presence of any plane of symmetry, what it is doing, it is dividing the molecule into two half. Okay, and you can see that this one half is the mirror image of the another, right? So this half, one half is mirror image of the another, and thus this is said to be optically inactive. They are said to be what? Optically inactive. Why it is optically inactive? Because the rotation which is produced by one half is uh, compensated by the other half of the molecule. And such a compound, they are called as what? Meso compound. So meso compounds, they are optically inactive. Why they are optically inactive? Because whatever the rotation is produced by the half of the molecule is compensated or it is cancelled by the other half. Why? Due to the presence of the plane of symmetry in the molecule. So such a compounds, they are called as what? Meso compounds. Okay. Very important. Mark this also as important. Meso compounds with a example. So what are meso compounds? So meso compounds, they are optically inactive. Why? Due to the presence of plane of symmetry in a molecule. So one half, so whenever the plane of symmetry is present, okay, so one half of the molecule is equal to the another half, and it is optically inactive because the rotation which is produced by one half of the molecule is compensated by the other half of the molecule. So such compounds, they are called as what? Optically inactive compounds. Okay, and these are termed as meso compounds. Okay, is it clear? What are meso compounds? So these are some of the important aspects, okay, which we are going to use, okay, which we are, so we have already seen SN1 and SN2 mechanism, okay, and there I have explained you also what is retention, what is inversion, okay. So like that, so these are also some of the important terms in chemistry when we are studying the stereochemical aspects, okay, how the arrangement of different molecules takes place specially, that is in the space, how we can rotate the molecule in space, okay. So these are some of the important terms, okay, which we are using, okay. So is it clear up to here? What are meso compounds? What are enantiomers? What are racemic mixture? What is a chiral carbon? What is a achiral carbon? Then we have discussed optical isomerism. Yes, so these all terms are clear. Okay.
Yes, ma'am.
Okay. Others? Okay. Fine. I hope. Okay. So what? So these things easily don't go in your mind. Okay. So what you have to do is you have to keep practicing it with the examples. Okay. So with examples, you can just practice them. Hmm. Now, what is optical active? Optical active means what? So it has the ability to rotate the plane polarized light, okay, towards the right or left. Now here, what is happening in meso compounds? You can see when a plane of symmetry is placed in the center, you can see that one half of the molecule is the mirror image of the other half, okay. So whatever the rotation which is produced by this is cancelled by the another, right? So this are said to be what? Optically inactive. they are said to be optically inactive because whatever the rotation is produced. Now, if the plane of polarized light is rotated towards right, okay, or clockwise, then it is dextro. If it is rotated towards anti-clockwise, levo. But here what is happening? Whatever the rotation is produced by one half is cancelled or compensated by the other half. So there is zero rotation possible. Okay. So such compounds are called as what? They are called as optically inactive. Why optically inactive? Because of this presence of plane of symmetry. Okay. So this is optically inactive. This is a meaning of optically inactive. Okay. So we have discussed, then was the retention. Now you know what is retention of configuration. So if the attack takes place from front side, okay. If the attack takes place from, suppose I have this molecule B. Okay, so if I have this molecule and what is happening, I'm attacking it with a nucleophile. So what is happening here? So B, okay, your Y and here is the C. So what is happening here? So is the configuration, is the spatial arrangement changed? The bonds are changed? No. Okay, only X atom has been replaced by the Y atom. Rest all bond arrangement are same. So if the relative arrangement, so whatever the arrangement, relative arrangement means what? The across the bonds, okay, the whatever the relative arrangement is there across this bonds, okay, at asymmetric carbon. What do you mean by asymmetric carbon? So the center carbon which is having four different groups, okay, so the relative arrangement at the asymmetric carbon, if it remains same, if it remains same before and after, so if the relative arrangement of the asymmetric carbon remains same after, before, okay, before the reaction and after the reaction, then it is said to be what? Retention of configuration. It is said to be what? Retention of configuration. So means what? In general, what we are discussing in retention of configuration, that no bond is broken at the stereo center. Okay. No breaking or no any bond is broken, right, at the stereo center. So the product, whatever the product is obtained, will have the same configuration as the reaction is proceeding, right? So it proceeds. So however, you can see that is at the starting reactant. Okay, what is happening in starting reactant also? At the starting reactant, okay, at the starting reactant, what is happening? It is the same configuration. In after reacting, also there is a same configuration. So this is called as retention of configuration. So no bond is broken at the stereo center. The relative arrangement of the atoms is same across the stereo center. Then it is called as retention of configuration. Okay. Next is inversion. Next is what? Inversion of configuration. Now, suppose I have this C2H5, okay, X CH3, X. So what is happening here? So C2H5, okay, so here it will be CH3, here it will be H, and here it is Y. Now here C2H5, here it is X, CH3, and Y. Okay. So what here we are doing? We are attacking the Y from behind. Okay. And here we are attacking it from front. Okay. So like this. So from like this. So what is happening? If A, so if I give this compound A plus B. Okay. This is a A compound. This is a B compound. So if A is only the compound obtained, then the process is called as what? If from this, okay, from this only A compound is obtained, then what it is called as? What you can see? If A is the only compound which is obtained, yes, when you compare this and this, what it is said to be? It is said to be then retention of configuration, right? So if A is only the compound which is obtained, then it is called as retention of configuration. Why? Only this is replaced. Okay. Now, if B is only the configuration, if B is only the B is only the compound from this process, then what you can see, then it is a inversion of configuration. Then it is called as inversion of configuration. Okay. So if this, so this 50% of inversion and this 50% of retention, okay, together they are called as what? So by this we are obtaining the A plus B compound, this one. So this is called as racemic mixture. It is called as what? Racemic mixture. And this process is called as racemization. And the product, whatever is obtained here, it is a optically inactive. It is a optically inactive. Okay, so these are the terms, important terms: retention, inversion, and racemic mixture. Okay, and racemic mixture. Is it clear? Yes. Okay, so let us study the stereochemical aspects in SN1 and SN2. Okay, so let us study the stereochemical aspects in SN1 and SN2. So fast. So now when I take the reaction like this, so we know SN1 reaction, it proceeds via stereochemical, means we have to represent spatially. Okay, so this you have studied in first year. Okay, what this represents? Bonds. Yes, this represents that this is near, okay, and this is far. So, and these are the two bonds, okay, near to the observer. So these all things you have studied. So first step is a slow step. It proceeds via a formation of carbocation. Okay, it proceeds via formation of carbocation. So this is the carbocation formed. Okay, plus Br minus. So this is a slow step. Step 1. Okay, then step 2 is what? Step 2 is a fast step. Okay, so what is happening here? So this is your CH3, H and C2H5. Okay, this is your tertiary carbocation. So what is happening here? So this is secondary carbocation. Okay, so what they have done, they have attacked the OH from behind and also from front. So you know that in when you are studying the stereochemical aspects, okay, so that time you will get a racemic of this, right, mixture, because the possibility is the attack can take place from front also and from behind also. So these are the products which are obtained. So this is the product if the attacks from here, and if it attacks from here, so that will be HOH. Then C2H5 and H. Okay, so this here it will be dotted line. So this is the stereochemical aspect. So if it attacks from front side, so it will be retention, and here it will be inversion. So a racemic mixture is formed. So SN1 reaction, okay, of a optically active halides, it is whenever we are studying the racemic stereochemistry of SN1 reaction, so it undergoes a racemization. Okay, because the carbocation which is formed in the first step, it is formed by a slow step, and that is sp2 hybridized. Okay, this is sp2 hybridized because you have a positive sign on the carbon, so it is said to be sp2 hybridized. Okay, and it is achiral. Why achiral? Because there are no different groups attached to the chiral center. Okay, so the nucleophile, it can attack from front side or it can attack from the back side. So what is possible? A mixture of product is possible. Okay, so one product with the front side and one product from the behind. So this is the example. Okay, so this is a stereo. So whenever we are studying stereochemical aspect, you have to write the racemic mixture. And whenever we are not, whenever we are writing them, they won't ask you for, but for understanding. Okay. But when you write SN1 mechanism, okay, just write the regular steps, what I have taught you. Okay. That it will undergo a retention of configuration. Okay. And stereochemically, you have to show what? You have to show the this what? Attack from both sides. That is a racemic mixture. So this is your CH3. Sorry, here that comes Br. This is Br. This is OH minus. Okay. You get CH3, OH and Br minus. So this is the first step. Sorry, this is a general step. So first step, you know, formation of carbocation. Then second step is attack of nucleophile and you get the retention of configuration. So whenever we are discussing stereochemically, that time you have to remember that the possibilities from both the steps. That is, it gives you a racemic mixture. Next is the stereochemical aspect in SN2 mechanism. Okay, in SN2 mechanism. So in SN2 mechanism, you know that, okay, the inversion of configuration is possible. So if I take the reaction like this, so CH3, H, okay, C6H13. So this is a minus 2 bromooctane, 2 bromooctane, okay, Br. So what will happen? The nucleophile will attack from behind and it will undergo what? Transition state, okay, and then it will form your inverted product, and the inverted product obtained will be like this. So CH3, then this will be in plane and this will be out of plane. So C6H13. So this is plus octane to all. Okay. So what is happening here? The nucleophile attack takes place from behind, okay, and at the asymmetric center, okay, and what it forms? And it forms a inverted product. So what is possible here? 100% inversion. And what is the type of inversion called as? What is the inversion in SN2 mechanism? What is the inversion? What is the name of the inversion seen in the SN2 mechanism? Important. Forgot? What is the name of the inversion seen in SN2 mechanism? It is called as Walden inversion. Okay, important. Mark this important. So Walden inversion is the inversion, okay, seen in SN2 mechanism. Okay. Can we list out some of the differences? Now we have seen what is SN1 mechanism and what is SN2 mechanism. Can we list out some of the differences between SN1 and SN2 mechanism, students? Yes. So let's list out this differences and then we'll stop. Yes. What is the differences between SN1 and SN2? So SN1, it follows what order kinetics? It follows first order kinetics. Okay, it follows what? First order kinetics. So here the rate of the reaction depends on what? It depends on the concentration of alkyl halides. It depends on the concentration of alkyl halides. Then your SN2 mechanism, it follows second order kinetics. Okay, second order kinetics. Here the rate of the reaction depends on what? Concentration of alkyl halides and the nucleophile as well as the nucleophile. Okay. Then second point is what? Second point is the SN1 mechanism. It follows two steps. Okay. Two steps with formation of carbocation. With formation of carbocation. Okay. Then here it follows one step with formation of transition state. With formation of what? Transition state. Okay. Then next step. Next is what? The order of reactivity of alkyl halides. So your tertiary alkyl halides are more stable than secondary, then primary, and then methyl carbocation. And here methyl carbocation, then primary, then secondary, and then tertiary. Then fourth one. Okay, so these SN1 mechanism, they are followed by polar solvents. Okay, so they takes place polar, or they are favored by polar solvent, and these are favored by non-polar solvents. Okay, non-polar solvents. And here, what is the product form? Product form is a racemic mixture. Okay, the product form is a racemic mixture. And here the product formed is what? The product formed is inversion. Okay, and what is the name of the product formed as a inverted configuration? And what is the name of the inverted product? It is a Walden inversion. Okay, it is a Walden inversion. So product formed in SN2 mechanism is what? It is an inverted product, and the configuration is called as Walden inversion. Is it clear up to here? Yes. So these were
Yes,
some
ma'am.
of the, yes, these were some of the stereochemical aspects, okay, of nucleophilic substitution reaction. So please note down this SN1 and SN2 mechanism, the differences. So these are very important. Okay, so up to here, everything is clear. Others? Okay, fine. Okay, then. So the remaining things we shall be discussing in the next class. I hope everything is clear. So please go, whatever we have, I have taught you today. So please go through all the things. Okay, if you have any doubts, you can come up to me tomorrow. Okay. Okay. So I shall end the session here. Okay, we'll meet in the next class. Thank you.